Hello, everyone. This video is on nomenclature, which is activity 2 in CHEM 100L. All right, so again, activity 2 on nomenclature. I thought it would be good to start a little before talking about nomenclature and reviewing how these compounds come to be or how they form and some important terminology, like the concept of ions. So many atoms form ions, and they do so through the transfer of electrons in order to have an octet, which is a stable number of electrons. So we typically say they want to have the same electron configuration as their nearest noble gas. So some ions typically are some compounds, or I should say elements. Okay, so use the right terminology here. Some elements, typically metals, will lose electrons to form cations. And cations are positively charged ions. And you can see that process is illustrated here. So M stands for metal. It is losing an electron, giving it to a nonmetal. And so this is a formal transfer of electrons. And the metal, which has lost an electron, because electrons are positively charged, when it loses an electron, it becomes, electrons are negatively charged. When it loses an electron, it becomes a positively charged ion called a cation. And the nonmetals typically gain electrons. You can see that this nonmetal right now has 7 valence electrons, and when it gains one more, it will have 8, right? So that's that octet that we were talking about. And because it has gained a negatively charged electron, it is now overall has a formal negative charge, right? And it is called an anion. So these ions are then attracted to one another through an electrostatic attraction, which basically means an attraction of opposite charges. And it's what that attraction is called an ionic bond. Okay, so we can determine the ionic charge from the group numbers in the periodic table for what we call group A elements. So in ionic compounds, we use these group numbers of some metals and nonmetals, and we get these group numbers from the periodic table, and they help us determine the charge for the ion. So for example, all of the elements in group 1A tend to lose one electron to have a +1 charge. Since there's only a 1 here, we just omit the 1 and we just say the element symbol and then just plus instead of +1. All of the elements in group 2A tend to form a ion that has a 2+ charge, right? Or a cation with a 2+ charge. So they tend to donate or give up 2 electrons to nonmetals to be able to form these ions. And then the most common one in group 3 would be aluminum, which will lose 3 electrons to have a 3+ charge. So these are all metals, right? And they tend to, again, give up electrons and take on a positive charge. And we can tell what that positive charge will be because the charge will match the group number. If it's a metal in group A, for transition metals, we do not determine the charge this way. So we do not determine the charge using the group number for transition metals, because those tend to form more than one type of ion, and we'll talk about those later. Nonmetals, which are more to the right on the periodic table, here are some examples from group 5A, 6A, and 7A. those tend to form anions, right, or ions with a negative charge. And depending on the group number, we can actually determine what sort of charge it is. But it's not quite as simple as with the metals in group 1A, 2A, and 3A, where the charge matches the group number. Here we can see that nonmetals in group 7A take on a -1 charge. And the reason for that is if they take on one additional electron, they will have a complete octet, and they will have the same electron configuration. So we say they're isoelectronic with their nearest noble gas. So nonmetals in group 7A tend to take on a -1 charge. Nonmetals in group 6A tend to take on a -2 charge. And then those in group 5A tend to take on a -3 charge. So oftentimes, right, with metals and nonmetals, excluding transition metals, we can determine the charge based on the group number. And here's another table from your book listing some common formulas and names of some common ions. So here you can see the group number, right, the different examples of ions that form from elements in that group, and then also the name of the cation. Notice that the name of the cation is the same as the element name. So the element name is lithium, and the cation is also called lithium. Whereas with nonmetals, the name of the anion actually changes, because the element would be nitrogen, but the name of the anion is nitride. And this name comes from the first syllable from the element name, so nitr, and then they drop the nitrogen, so they drop the ogen, and then add the suffix "ide." And you can see some common examples here. So again, right, to review, in an ionic compound, one or more electrons from metals is transferred to nonmetals, and that forms cations and anions. And there's an electrostatic attraction between those that forms an ionic bond. But the ionic compound has very different chemical and physical properties from the element from which it derives. So for example, sodium chloride, which is an ionic compound composed of sodium cations and chloride anions in a three-dimensional array, right, in the crystal structure, because this is a white crystalline solid. This has very different properties from sodium metal, which is the elemental form of sodium, and chlorine gas, right, which is the elemental form of chlorine. Sodium metal is a soft white solid, and chlorine gas is a poisonous yellow-green gas. And so those are very different from the properties of sodium chloride, which is common table salt and an important part of our diet. Okay, so let's talk about chemical formulas of ionic compounds. So recall that sodium, which is in group 1A, will commonly lose one electron to form sodium plus. That electron can be given to an element such as chlorine. And when chlorine takes another electron, it becomes Cl minus, which we call chloride. So after the transfer of one electron from sodium metal to chlorine to form sodium ion, sodium plus cation, and the chloride anion, right? Now we have the ionic compound sodium chloride, which can be written as NaCl. Because sodium has a 1+ charge and chloride has a -1 charge, those balance each other out so that the net charge of the ionic compound is 0, which always needs to be the case, and we call this charge balance. So again, the NaCl is the chemical formula. Sodium chloride is the chemical name. The formula represents the lowest whole number ratio of the ions, which is just in this case 1:1. Ionic charges are not shown in the formula. So notice the plus and the minus, right, are not found in the formula here. We know what the charge is because this ionic compound must have charge balance. And since sodium is +1 and chloride is -1, it must be 1:1. So we do not need to include subscripts here to show 1:1. If it's 1, the 1 is just omitted and assumed. So if you don't see any subscript, you can assume that there's just 1 of that type of ion. Sometimes we do use subscripts though, and that's when there is more than one ion. So again, if it's 1, it's omitted. But if it's 2 or more, then we use a subscript in the formula. So notice down here we have magnesium chloride, which is written as MgCl2. This is formed from magnesium metal, which loses 2 electrons to form a magnesium 2+ ion. These 2 chlorines gain 1 electron each to form chloride ions. So for charge balance, because the magnesium is +2, we need 2 chlorides to balance out the +2 charge. That is why you see the 2 chlorides here, right, for a total of a -2 charge to balance out the +2. Because there's more than one chloride in this ionic compound, we do now use the subscript 2, right? So this denotes that there are 2 chlorides for every 1 magnesium cation. Let's look at another example. In this case now we need 2 sodium metal atoms to donate 1 electron each to a sulfur atom, forming sodium cations and a sulfide anion, right? So because the sulfur normally has 6 valence electrons, it needs 2 more electrons in order to get an octet, which again is that stable number of electrons isoelectronic to its nearest noble gas. So because it tends to form an ion with a -2 charge, and it's going to be attracted to sodium ions, there needs to be 2 of these to balance out the charge overall in the compound. Because 2+ will balance out 2- for a net charge of 0. Because we needed 2 sodium cations, we do use this subscript 2. So we write Na2S. Notice that if when we look at the symbol here, right, if there's only 1 letter, it's always capitalized. If there's 2 letters, the first letter is capitalized like this capital N, and the second letter is lowercase. All right, let's move on to some nomenclature. So now our goal is going to be to name and write ionic formulas. So what is our learning goal? Our learning goal in this section is, given the formula of an ionic compound, we want to be able to write the correct name. And given the name of an ionic compound, we want to be able to write the correct formula. So we're going to be starting off with what are called type 1 ionic compounds. And in type 1, the metal only forms 1 ion. So this is going to be the simplest type of ionic compound because the metal used is only forming one ion. So it's really clear as what the charge is going to be on that ion, since that metal only forms one ion with one specific charge. So when we write the name, the metal name is written first, and it's the same as the element name. So for example, if we were to see Ki here, right, the K stands for the potassium ion, K plus, and the name of the element is potassium, and the name of the ion is still potassium. The nonmetal name is written last, and it uses the first syllable of the element name followed by the suffix "ide." So the I here stands for iodine atoms, right? But we don't call it potassium iodine because the anion has a different name. Again, we use the first syllable in the element name, so iode, right? And then we drop the INE and add IDE. So this becomes potassium iodide instead of potassium iodine. Notice that there's a space that separates the cation and the anion name, and we do not use any prefixes for subscripts. So even if there are, for example, 2 bromides here, that is not indicated in the name. For example, we don't call this magnesium dibromide. We don't need that prefix di, it's just magnesium bromide. The charges on the ions are understood because we know that these ions have to be in charge balance. So let's look at a image I got from your lecture textbook. And this shows that the type 1 metals that we're going to be dealing with are those that are in group 1A and group 2A. Notice they all form only one ion, right? No, meaning that there's only one charge. Like lithium only forms lithium +1 or Li plus. It doesn't form 2+ ions or 3+ ions or any other type of ion, right? Those that are in group A always form 2+ ions. And these are just listing the most common ones here in this particular image. And then notice that it's also common to see aluminum in ionic compounds forming Al3+. So there's a few in the transition metals that also only form one ion. And so those are also considered type 1 metals. For example, zinc only forms a 2+ cation. Cadmium also only forms a 2+ cation. Silver only forms a 1+, right, ion. And so those are also then included in type 1 because they only form one ion. Some of these others are going to form more than one ion, and we'll talk about those later. Those are called type 2 metals. But we're starting with type 1, excuse me. Okay. So let's do some sample problems. So in this problem, we're going to be starting with the formula of an ionic compound and coming up with the name. So that's our goal, is to be able to write the name for this ionic formula. Okay, so what are the steps involved for these type 1 ionic compounds? Well, step 1 is going to be to identify the cation and the anion. And so we're going to be able to find those by looking at which group they're in the periodic table. So for example, Mg stands for magnesium. And we can find that in group 2A, and it forms magnesium 2+ ions. Nitrogen will form nitride. and nitride is in group 5A, which tends to form 3- anion. So it's N3-. So we need to identify the cation and the anion, right? And then determine the name based on the cation and the anion. Remember that the name of the cation is the same as its element name. The name of the anion is the first syllable of the element name followed by the suffix "ide." And then we write those together, putting a space between the cation and the anion. So I encourage you guys to pause the video, try to do this yourself, and then continue the video where I go over the answer. Okay, hopefully you've tried to work on it yourself, and now we're going to go over the answer. So again, we talked about the fact that the first step was to identify the cation and the anion. We know that magnesium only forms one ion, Mg2+, and the anion is N3-. Mg2+ is just named the same as its element, magnesium. N3- is named nitride, comes from nitrogen, where we only take the first syllable in the element name followed by the suffix "ide." Putting that all together, we write the cation name first, followed by the anion name with a space in between. So it becomes magnesium nitride. Let's do another problem. In this case, we're going to go from the name, which is given to us, and the goal is to write the correct formula given the name. So again, step 1 is going to be to identify the cation and the anion. And then based on the charges, we need to figure out how many cations and how many anions are needed for charge balance. And remember that the lowest whole number ratio is the one that we're going to use. Step 3 will be to write the symbol for the cation first and the symbol for the anion second, with subscripts if needed. So aluminum, right? So we want to go to the periodic table, figure out the symbol for aluminum, which is Al, right? And then figure out the charge on that. Aluminum only forms one type of ion, which is Al3+. The anion is chloride, right? So chlorine is in group 7A, right? And it forms Cl- as a result. I'll stop there and let you guys work out the rest of the problem by yourself. Remember, pause the video, try to do it yourself, and then see if you get the same answer that I'm going to go over in just a minute. Okay, so hopefully you try to do this yourself. So remember, the first step was identifying the cation and the anion, which I helped you with before. And then based on the charge, we determine how many of these ions are needed. So aluminum has a 3+ charge, and chloride only has a -1. So 3 of chlorides are needed to balance out the aluminum's 3+ charge. So the number of cations needed is 1, the number of anions needed is 3. And then this becomes the subscript that's used in the formula. Remember that 1, if the answer is 1, that's omitted. You don't need to write Al1, right? We just write AlCl3, with the 3 being subscripted. Now, when you're entering this into Canvas, there is no way to subscript number, so we just don't even try and just write a regular 3. But remember to always make sure to read the instructions for exactly how to input the name or the formula so that Canvas will mark your answer as correct. Okay, so I included this just to show you that Of course, you guys are just starting out in chemistry, so you don't know all of the element names and symbols. So it's useful to have a periodic table like this around where you can look up an element name or symbol to go between them. So for example, if you didn't know what N stood for, you could find N on this periodic table and know that the element is nitrogen, right? Or if you were looking up something you've never heard of before, like platinum, right? Maybe you'd come in and find platinum and then note that the element symbol for that is capital P with a lower case t after it. All right, so next we're going to talk about polyatomic ions. And our learning goal is to write the name and formula for an ionic compound containing a polyatomic ion. So I included this table here, which lists some common polyatomic ions. And they're exactly what they sound like, right? They're ions, meaning that they're charged, but they're made up of poly, which means many, atomic, so many atoms, right? So notice that it's not just one atom that has a negative charge, right? It's a group of atoms that have a negative charge. And so here's some formulas and names for some of those. Okay, so again, a little bit more on what exactly is a polyatomic ion, right? Well, it's an ion, so it's a charged species, and it consists of two or more atoms covalently bonded together. So that's a new term for us, covalently bonded. That means that the atoms are sharing electrons instead of having formally transferred electrons from one atom to another. So basically, these lines here are indicating that the atoms are actually sharing some of their valence electrons, and that's a type of bond called a covalent bond. So it's a group, right, of at least two atoms that overall has a charge. And they're almost always a negative charge, except for ammonium, which is the one case where it's a polyatomic ion that happens to be positively charged. So this is the only cationic polyatomic ion. So here are some examples of ionic compounds that contain polyatomic ions. So for example, calcium sulfate. SO4 2 minus is a polyatomic ion called sulfate. And it is used to make plaster casts. You can see here, right, there's a sulfur, which is colored yellow in the center, right, with 4 oxygens around it. And overall, this entire thing has a -2 charge. And fertilizer, right, one type of fertilizer is called ammonium nitrate. Ammonium nitrate is actually made up of 2 different polyatomic ions. We have ammonium, which is NH4 plus, and nitrate, which is NO3 minus. And you can see that overall, again, it's the more than one atom covalently bonded together, which overall has a charge. So again, ammonium is the only cationic polyatomic ion. Most are anions, which involve a nonmetal, such as phosphorus, sulfur, carbon, nitrogen, covalently bonded to oxygen atoms. So notice the sulfur with 4 oxygens, the nitrogen with 3 oxygens, right? So that's a common bonding pattern for polyatomic ions. So here's just a couple more tables that I thought I would include, which come from your lecture textbook and just one I found online that lists some common polyatomic ions, because as you're answering the questions, you will need to look up some of these to be able to answer these questions. So having these tables is really helpful. I also wanted to include this sort of more comprehensive chart because there are a few on the activity that are a little bit harder to find. So I wanted to make sure that you had this resource that has, pretty much any polyatomic ion that you might need to find should be on this list. So for example, arsenite is needed in the activity, and that's kind of a difficult one to find. So I wanted to make sure to include that, as well as biphosphite and phosphite. Those are needed, I believe, as well. So wanted to make sure you had this really, really comprehensive list. And don't be too confused with acetate. Sometimes this is written differently. It's okay either way. So sometimes it's written CH3COO minus, and then I think in your lab manual, he has it as C2H3O2 minus. So if there's any in there, and you end up doing it either way, I will go ahead and make sure to correct that in case you're marked wrong. Okay, so let's talk about writing formulas for compounds containing polyatomic ions. Sorry, I'm gonna put one of these cough drops in my mouth. I'm a little sick today, but I have to make this video, so I am doing my best here. Okay. So if our goal is to write the correct formula for a compound containing a polyatomic ion, we need to follow the same rules for charge balance that we used for writing the formulas for simple ionic compounds. Meaning that the total positive charge of the cation and the total negative charge on the anion must still equal 0. So let's consider the formula for a compound containing sodium ions and chlorite ions. So we know the formula for sodium ions is Na+, and we can look up chlorite and find that it's ClO2 minus. So the charge balance is simple here because +1 will balance out -1 for a net 0 charge. Because there's only one ion is needed of each, right? And that has charge balance. The formula is just written where we start with the symbol for sodium, Na, followed by the symbol for chlorite, which is ClO2. So we just put the metal first, followed by the non-metal. Now, it's possible that in some cases, more than one polyatomic ion is needed. So for example, if we consider a compound formed from magnesium ion, which is Mg2+, and nitrate ion, which is NO3-, we notice that in order for charge balance, we need to have 2 nitrate ions balance out the single magnesium 2+ ion, so that we have a net 0 charge, because 2 negatives will balance out 2 positives. Which means that we need to indicate that there are 2 nitrates in our ionic formula. So again, we start by writing Mg, which is the symbol for magnesium. And then we need to write that there are 2 nitrates. In order to do that, we put the NO3 in parentheses. Remember that the charges are not included, right? Because we just write the how many there are, right, as a subscript. So this is indicating that there are 2 of everything that's in parentheses, which is the nitrate ion. Okay, let's do sample problem number 3, which are examples is an example with a polyatomic ion, or in this case, 2 polyatomic ions. So this is an example where we're given the formula and we're asked to come up with the name. So the steps are to identify the cation and the anion. And in this case, both of those are polyatomic ions. So we just want to come over here and say, okay, which one is NH4, right? And I come over here and look and I see, okay, NH4 plus is ammonium. And then PO4, where can I find that in my list over here? Right, so PO4, I see it right here. PO4 3- is phosphate. So we can identify the cation and the anion and identify their name, and then put the name together, writing the cation first and the anion second. So I'll give you guys a minute to try this for yourself. Pause the video and then resume when you're ready to go over the answer. Okay, so again, we first needed to identify the cation and the anion, both of which in this case are polyatomic. So we found out that we have NH4 plus and PO4 3-. NH4 plus is called ammonium and PO4 3- is called phosphate. So putting this together, we write ammonium with a space and then phosphate. Remember, when you're entering these into Canvas, spelling counts, right? You have to spell these words correctly in order for this to be marked correct. I guess I should point out that we did not have any indication of how many ammoniums and how many phosphates are in the formula. And that's again because we assume that there's charge balance. So we don't need to indicate that information because we know that phosphate has a 3- charge. So there must be 3 ammoniums because ammonium only has a +1 charge in order to balance out the 3 phosphates. And that's actually, that information is provided in the formula. We see that there are 3 ammoniums for every 1 phosphate. So that information is provided in the formula, and it doesn't actually, it's not necessary to write how many there are in the name, right? Because that's implied information from the formula. All right, let's go ahead and do sample problem number 4, which is another example with a polyatomic ion. So again, in this case, we're going to be starting with the name and then asked to write the formula. So we're given barium bisulfate. So barium is not a polyatomic ion. It is a type 1 metal ion, which only forms 1 charge, and we can look it up on a periodic table. But bisulfate is a polyatomic ion, and so we want to look on one of the tables that contains polyatomic ions to find it. Right, so identify the cation and the anion in terms of its formula and its charge. Based on that, because we're writing the formula and we are going to need to include, potentially include subscripts, then we need to know how many cations are needed for charge balance, how many anions are needed for charge balance, right? So that we use the lowest whole number ratio. When we're writing the, sorry, this should not say write the name. It should say write the formula for the cation first and the formula for the ion second. Sorry, I'll change that in the slides. Okay, so it's helpful if we need to look back at a periodic table to be able to find barium, right? And we see that it's in group 2A, so it is barium 2+. So barium 2+, right, is the cation, And then we wanted to find bisulfate. You could actually find it over here in the table. Sometimes it's called hydrogen sulfate, right, or bisulfate. If you were putting in the name into Canvas, either one would be accepted. Either one is listed as a correct answer. But if you were writing hydrogen sulfate instead of bisulfate, you would need to put a space between hydrogen and sulfate. Okay, so anyway, the formula for that is HSO4-. So we see that the anion has a -1 charge, the cation has a 2+ charge. So we're going to end up needing 2 of the polyatomic bisulfate ions to balance out 1 barium cation. So we need to indicate that in the formula. And again, this should say write the formula for the cation and the formula for the anion. Second, so we write Ba for barium. Parentheses are needed around HSO4 because we need 2 of them. So if we need 2, we have to use parentheses to be able to place the subscript 2 outside of those to indicate that 2 bisulfates were necessary to balance out the cation. Okay, so let's talk about sort of where we're at right now, where we're going next, and what we'll talk about last. So far we have talked about naming ionic compounds, which are formed from a metal and a non-metal that have formed ions, right, and are attracted to each other as a result of their opposite charges. So the metals that we've seen are either single atom or polyatomic in the case of ammonium. So those typically form our cations. And we've been looking at type 1, where the cation only forms 1 type of positive ion. So the name for that is just the same as the element name, or ammonium, in the case of that polyatomic cation. For nonmetals, right, which tend to form our negatively charged anions, we have seen monatomic ions and polyatomic ions. The polyatomic ions, we just use the name of the polyatomic ion. For the monatomic ions, we use the first syllable of the element name followed by the suffix "ide." So that's what we've covered so far. Next, we're going to talk about type 2 ionic compounds, which form more than 1 positive ion. And for those, we're going to be using Roman numerals that are equal to the element charge in parentheses as part of the cation name. After we talk about those, we'll move on to molecular compounds, which are formed between 2 nonmetals. So again, now we're going to talk, the next thing we're going to talk about is type 2 ionic compounds, which contain metals that form more than 1 ion. So for example, here we can see iron chloride, and but we can't just say iron chloride because iron forms more than 1 type of ion. Iron can form iron 2+ and iron 3+. So in order to write the name correctly, we need to write iron, parentheses, Roman numeral 2, close parentheses. This is the cation name. And we know that because there's 2 negatively charged chloride ions, -1. 2 of those is -2, so the iron must be +2. Here you can see iron forming a different ion. Iron also forms 3+ ions, which you can see here in iron oxide. And there's lots of other transition elements like copper, chromium, tin, lead, and bismuth that form more than 1 ion. And so these Roman numerals in parentheses are necessary so that we know exactly what ion is being used to form that particular compound. So again, we cannot determine the charge of most transition elements using the group number. because for the most part, with a few exceptions, they typically form 2 or more positive ions. So a Roman numeral that is equal to the charge is placed in parentheses after the name of the metal. And again, the name of the metal is still the same as the element name. So for example, iron 2+ is iron 2. Iron 3+ is written as iron Roman numeral 3 with parentheses around it. There are some transition metals such as zinc, cadmium, and silver, which only form one ion. So those are considered type 1, right, where we do not need parentheses with charge, because if it only forms one ion, it's clear what ion is being included in the formula. And then, of course, we also will have a nonmetal, which is our anion. It will be written last, and the same rules apply as with type 1 compounds. We're going to use the first syllable of the element name followed by the suffix "ide." So here's another look at this picture, which shows some of the common transition metals that form more than one ion, right? So for example, copper here, which forms +1 and +2 ions. So this would be an example where we would need to include that Roman numeral with parentheses to make it clear which ion is in that particular formula. Here's another table from your lecture textbook that shows some metals, right, that form more than one ion. And then the tricky one actually are the mercury ions, because they actually have the same charge, right? They both have a 2+ charge, but Hg2 2+ is actually called mercury 1, and it's because it's an ion pair, or kind of like a dimer. So there's 2 mercury 1 ions that form an ion pair, right? So overall they have a 2+ charge. So that one's a little bit tricky because the charge is the same, but you can tell the difference whether or not it has a 2 here or not, right? So this subscript here. So no 2 is actually mercury 2. And then if you see mercury with the subscript 2, that's actually mercury 1. So that one's a little tricky, something to commit to memory there. Okay, so how do we know, if we're given the formula of an ionic compound, what the charge is going to be on the metal if the metal can form more than one charge? Well, the charge is determined by the negative charge of the ions in the formula. So for example, if you see CuCl2, right, we know that we have an anion here, which is chloride. Chloride is Cl-, and there are 2 of them, which means that there is an overall -2 charge because there's 2 Cl-. So for charge balance, this must be Cu2+, because a 2+ charge is needed to balance out the overall 2- charge on the anions. If you saw Cu2Cl2, right, then we would know that each copper should be Cu+, because there are 2 of them, which would overall be +2, which would balance out the -2. But since there's no subscript with a 2 here, this one single ion must have all of the positive charge that balances out the negative charge. So it has to be Cu2+. So the name then, we write copper. Immediately after that, a parentheses, Roman numeral 2, close parentheses, space, then the word chloride. And to this list, you can add platinum, which forms platinum 2+ and 4+ ions. That will be a helpful one to also have to be able to do the problems in the activity. All right, let's go over another sample problem. And again, now we're dealing with type 2 compounds, which contain variable charge metal ions. And the first type of problem is going to be starting from the formula. Our goal is to be able to write the correct name. So we see here, right, CO, that stands for cobalt. And cobalt forms more than one type of ion. It can form 2+ and 3+ ions. So we don't know which one we have, and our goal is to figure that out, right? So when we're dealing with variable charged metals, we actually want to start with the anion, because the overall charge from the anion will tell us what the charge must be on the cation. So start with the anion, right? This N here, right? Figure out what that formula is and what charge is associated with that formula. So this is a group, this is in group A, right? So just by looking at the periodic table, you can determine the charge here. And then from there, given that there's 2 of them, figure out overall how much negative charge there is. And given that there's 3 cobalt ions, what must be the cation there? So it's a little bit tricky. We start with the anion. We have to know what charge is associated with that anion. We see how many there are to give us the total negative charge. Then we want to figure out, okay, what's going to be the charge on the cation, which is the cobalt? Well, I know that there are 3 of them. And overall, how much positive charge I have needs to balance out perfectly the amount of negative charge. Right? So once we determine that, we can figure out the name of the cation, the name of the anion, and then put those 2 together to come up with the final name. And don't forget those Roman numerals, right, and parentheses, since cobalt is a variable charge metal ion. All right, I will go ahead and pause so give you a moment to work on the this, and then when you're ready to go over it, go ahead and resume the video. So go ahead and pause right now. All right, hopefully you tried it yourself and you're ready to go over the answer. So again, we needed to start with the anion, right? And it showed us that it was nitrogen, which we call nitride, right? And since it's in group 5A, it typically takes on a -3 charge. So we know now what the anion is. Cobalt could be cobalt 2+ or cobalt 3+, and we'll keep that in mind. But because we know the charge on the anion, we'll be able to figure out the correct charge on the cation. So the anion is N3-, and from the formula we know that there are 2 of them. So if there are 2, the total charge is -6 for the anions. That means that the total charge for the cations must be +6. Since there are 3 cobalt ions, right, 6 divided by 3 is 2. So that means that we must have had cobalt 2+ ions, because if we have cobalt 2+ ions and there are 3 of them, that will give us a total +6 charge. It can't be cobalt 3+, because if it was cobalt 3+ and there were 3 of them, that would give us a total +9 charge, which would not balance out the -6 charge on the anions. So cobalt 2+ is named cobalt, parentheses, Roman numeral 2, close parentheses. And N3- is named nitride. So this, putting it all together, we write cobalt 2 space nitride. Let's look at another example with that tricky mercury, right? So again, it's another example where we're going to start from the formula and our goal is to write the name. So anytime you're using, if you have a variable charge metal ion, we always want to start with the anion. From that will help us typically figure out what the cation charge must be. So I'm not going to give you any hints on this one. I'm just going to let you try it yourself, and then we'll go over the answer. Go ahead and pause the video, try it yourself, and then resume when you're ready to go over the answer. All right, so we saw Hg2O was the formula that it gave us. So if we start with the anion, we know that O2 minus, which is called oxide, right, is what the anion is. So that's helpful information to be able to figure out which mercury we're using. But in this case, this is the tricky one, right? Because both of them have an overall +2 charge. The difference is this little subscript 2. So if you see that in the formula, Hg2, then it must be mercury 1, right? If there wasn't a 2 there, then it would be mercury 2. So that's the difference. So putting this all together, the anion is O2 minus, which we call oxide. There's only one of them since there's no subscript after the O. So our overall negative charge is just -2, which means that it makes sense that there's only one cation. Really, it's a dimer of 2 mercury 1 ions, right? That overall has a +2 charge. So we know it's Hg2, 2+, because of this subscript 2 here. And we know that Hg2 is actually called mercury 1. So putting it all together, we have mercury, parentheses, Roman numeral 1, close parentheses, space, oxide. All right, let's do a problem number 7, which is another problem using variable charge metal ions. But now we're going to be starting with the name and working towards generating the correct formula. So they've given us chromium 3 carbonate, right? So going this direction is actually much easier because the Roman numeral has told us the charge on the variable charge metal ion. It has told us that the cation is chromium 3+, right? Carbonate is one of our polyatomic ions, so we want to go to a table that includes polyatomic ions to figure out that carbonate is CO3 2-. Okay, what you're going to want to do is balance the charges. So determine how many cations are needed, how many anions are needed for charge balance. And then step 3 will be to write the formula cation first, using subscripts from the charge balance, and use parentheses if there is more than one polyatomic ion. So go ahead and pause it, try to do this one yourself, and then resume and see if you got the right answer. Okay, so again, we'll take a look at this chart here and see that chromium, the formula is capital C little r, right? And we know that it can form 2+ ions or 3+ ions, but it said chromium 3, so we know we're dealing with chromium 3+. So we'll go ahead and write in here that the cation is chromium 3+, and the anion, right, carbonate, is CO3 2-. So now we need to figure out how many cations are needed and how many anions are needed for charge balance. Remember, we want the lowest whole number ratio. So chromium 3+ and CO3 2-, right, we have to multiply the 3+ times 2 to get overall 6+, so that we can balance out the 2- by multiplying by 3 to get 6-, right? So notice that the charge here, 2- becomes the subscript, right, for the other ion. So these subscripts are needed, right, when we're writing out the formula. So we write Cr2 because we know we need 2 chromium 3+ ions to balance out the 3 carbonate ions. And since there's 3 of a polyatomic ion, we have to use parentheses, right, around the CO3, and then write a 3 outside to denote that there were 3 of those ions needed. So remember, the subscripts really tell us what the charge is on the other. Okay, the last type of naming we're going to do today is on molecular compounds, which are compounds that are formed from electron sharing rather than electron transfer. The learning goal for this section is going to be given the formula of a molecular compound, write the correct name, or given the name of a molecular compound, write the correct formula. So now we're moving over here to this part of our flowchart, where we're naming molecular compounds that are formed from multiple nonmetals. So we have the first nonmetal and the second nonmetal. And we are going to be using prefixes to match the subscript before the element name. And that's because there are multiple ways that nonmetals can combine in order to make molecular compounds. So it's important that we use these prefixes to denote how many there are. And that'll make more sense once I show you an example of what I'm talking about here. The second nonmetal, we still are going to use a prefix. And just like with ionic compounds, we're going to use, we're going to end with an "ide" at the end. Okay, so looking back at this picture here, now we're over here to the right where we're looking at 2 nonmetals that can also form bonds. But neither nonmetal is really inclined to give up its electron to the other nonmetal. So instead of the formal transfer of electrons, when nonmetals bond, they tend to just share their electrons. And we call this sharing the formation of a covalent bond. And here are some examples, right? So we have both carbon and oxygen are nonmetals. So when they bond together, they form this type of molecular compound. CO2 is called carbon dioxide. We're going to talk about this di prefix in a minute and why we use that. But carbon dioxide, you may know, is used in fire extinguishers. It is in solid form in dry ice, right? It forms the bubbles in your soda. And so here's just a variety of other ones. I won't talk about them all. You can read through them on your own of different molecular compounds and what their uses are. They're very interesting. But let's talk about naming a little bit more. Like, where did that di come from in carbon dioxide? Okay, so the first nonmetal is just named using its element name. So same as when we did ionic compounds. The second nonmetal is named using the first syllable of the element name followed by the suffix "ide." So again, very similar to ionic compounds. The difference is that now when we have subscripts that indicate that we have 2 or more atoms of an element, we are going to start using prefixes, right? That are those that are shown in this table over here in front of the name. And these prefixes are necessary because molecular compounds formed from nonmetals tend to form more than one compound formed from the same elements. So for example, carbon can bond with 1 oxygen, or it can covalently bond to 2 oxygens. So if we just write carbon oxide, it's not really clear how many, right, carbons and how many oxygens are there, right? Is that going to be CO or CO2? We don't know. And remember that these are not forming ions. So we're not looking at oxide as in O2 minus, right? They're sharing electrons in this case as opposed to forming ions. So we can't just look at charge to figure out what the subscripts would be. That's why we use these prefixes with molecular compounds. So now if I tell you the name of CO is carbon monoxide and the name of CO2 is carbon dioxide, then you can say, okay, well, the mon or the di tells me how many oxygens are in the formula, right? So you can see the different prefixes that are used to denote how many of that type of atom of a particular element are in that molecular compound. Now, just like when we write formulas and we often omit one, just don't write anything, right? The prefix for one, which is mono, is commonly omitted, except for carbon monoxide, in which case it's put in to make sure that it's clear that it's not carbon dioxide. But other times that there is one oxygen, for example, it would just be called oxide. For example, NO would be just nitrogen oxide, not nitrogen monoxide. So mostly mono is omitted, except for in one specific compound, which is carbon monoxide. And then another important spelling rule is that when you have two O's that come together from the prefix and the element, or an A followed by an O, the first vowel is omitted. And you can see that with carbon monoxide. So this is not written MONOOXIDE, right? The first O in mono is omitted. So it's just mon and then the word oxide. So again, you don't put two O's or an A followed by an O. The first O or A would be omitted. Okay, let's look at some examples. So hopefully this will make a little bit more sense. So sample problem number 8 on molecular compounds. So we are doing a problem where we are starting with a formula and we are asked to write the name. So what we need to do is look at the symbol here and identify what the first nonmetal is and what the second nonmetal is. And then using this subscript 4, we'll come over here and look up 4, right? We indicate that with the prefix tetra in front of the second nonmetal. Okay, so go ahead and pause it here. Try to do this one yourself. And then when you're ready, resume the video and we'll go over the answer. All right, hopefully you've given this one a shot. So we had C, which stands for carbon, and Cl, which stands for chlorine, right? And again, using this type of periodic table where you have the name and the symbol, right? It's helpful in case there's one that you don't know and you need to look it up. Okay, so again, the first nonmetal, which is indicated by just this C here, is carbon. The second nonmetal, Cl, is chlorine, but we call it chloride in the name because, again, we add the suffix "ide" after the first syllable in the element name chlorine, which is just chlor. And then in molecular compounds, we need to add prefixes to indicate the number of atoms. Remember that if there's one of something, we often omit the mono. So this is not monocarbon, this is just carbon because we don't need to write mono except in the case of carbon monoxide. So it just becomes carbon, and then since there's 4 chlorides, we call that tetrachloride. Let's look at another compound. This is another example of a molecular compound where now we're going from the name and asked to write the formula. So they've given us the name. So for now, we're going to ignore this di. Later on, we will use that as a subscript after the element. But our first nonmetal is phosphorus. So we need to look up the symbol for that. And then we have pent oxide. So notice that the A was dropped here from penta. So it just became pentoxide. And we want to, again, first look up what's the symbol for oxide, which comes from oxygen, right? And then we're going to put those together, the first nonmetal followed by the second nonmetal, and then using these prefixes will become our subscripts, right? To tell you how many there are. Again, if it was just one, we wouldn't need to include that. So go ahead and pause it here, try to come up with the formula for this one. And then when you're ready, you resume the video to see if you got the right answer. All right, hopefully you worked on it yourself a little bit. So we had phosphorus and oxide, which comes from oxygen. So we want to know those formulas. P for phosphorus, O for oxygen. And then we need to include di means 2, so we write P2. Pent means 5, so we write O5. So diphosphorus pentoxide is P2O5. And then I just wanted to include some extra tables here in the PowerPoint slides that I found in your book that it may also be useful for you. So again, here's more formulas and names of some common ions, including some variable charge ions as well. And then here's some more, including some polyatomic ions. All right, so that's the end of the tutorial. As always, I hope you're working on this early in the week so that if you have any questions, you can pop onto an office hour this week and ask me, and I can help make sure that you are going to get the right answer. In Canvas this week, I believe you have 3 attempts at filling out the worksheet. So you have to actually input the names and the formulas. It gives you explicit instructions on how to do that. So when you're writing the name, don't capitalize the first letter, just all lowercase. Make sure to put spaces in the right places, things like that. So make sure you're paying attention to those instructions so that you input it correctly so that Canvas marks it as correct. But any ones that are marked incorrect, you still have 2 more attempts to be able to write those in. And whatever you do write, make sure you have a copy of it in case you need to do more attempts and you know you got that one right, you can just easily copy. Make sure that you're spelling everything correctly, because that's another way that you can get marked incorrect, is if you didn't spell things correctly. And then the big thing with the subscripts, so normally you would see subscripts, right, as smaller than the symbol. We can't do subscripts in Canvas, so you're just going to have to write it without subscript. So if you have any questions about how to input these into Canvas, also let me know and I can help you out with that as well. So good luck, and please seek support if you need it. Thank you.